Next, we'll talk about expected value. Now, before we talk about expected value, I want all of you to read this. Go ahead and read this. Okay. All right. So, what did you understand? So, this is about a particular game where they have decided that there is a coin, and whether the coin gets an H or a T upon flipping, they have this deal that if there is an H, the first player will pay Q, and if it is a tail, then the other player will pay R. All right. And using probability, what they have tried, where they have tried to find an average value that each player will get, or sorry, the first player will get. The first player, which is like paying R, I guess. Sorry, yes, the first player is who pays R and gets Q. Okay. So depending upon the probabilities expression, like what it has been written here is the n in this expression is inconvenient. If we do not want this to be inconvenient, we can simply take an average of this value. So this is the sum of the income that it would receive over the n games. We divide it by n, then we get a income for single game. Okay, the average value of income. So if you closely look at this value, this is a fairly complicated expression. However, we can intuitively see that when we flip a coin, if it is heads, we will uh, get Q, and if it is tails, we will lose R. So our income will be either Q or minus R. And this is nowhere related to this particular expression here. However, this is what we call expected value of a variable for any particular sample, for any random sample that we take. So given a random variable, we can have such an expected value. Okay. And this is how we write it. So this is a notation. Actually, the notations that is generally used in books is something like this. But it is difficult to draw. That's why I prefer to draw it like this. Okay. So the expectation of a random variable x is equals to summation x over d. What is d? D is the complete range of x. So the set of all values that x can take, all possible small x. Okay. The summation over d of x dot px. All right. Probability of x taking the value x multiplied by the value summed over d. So this is the expected value that we propose to get. Okay. And what does this expected value gives us? It gives us an estimate of a value of random variable over the complete range of values. Okay, given a probability distribution P. So let's say once we have identified that how X behaves, and how did we do that? By knowing or by deriving P. When we identified P, what we said, that we are trying to identify or trying to know that how X behaves or how X is distributed. So now that we have this P, then next what we are interested in is that what is the expected value of X. Okay, given the complete range of values that it can take for any number of experiments, not for just any particular experiment, or not for any the first experiments or the last experiment or the third experiment. Let's say if n number of experiments take place, and here that n is the complete range of x. So for all values of x, if we consider the probabilities of such values, what will be the expected value of x? Now it is important to understand that this expected value is just an estimate, and it need not be present in this set here. For example, let me give you an example for this. So let's say we flip a coin, okay, and the coin can be heads and tails. Okay, for a head, let's say we add 1 to our sum, and for a tail, we add -1 to our sum. Okay, erase all. Get some space. So we are flipping a coin, and for each flip, we are adding either 1 for heads to our sum and -1 to our sum for tails. And since it is an unbiased coin, the probability of heads will be 1 by 2, and the probability of tails will also be 1 by 2. So depending upon that, using this formula, what would happen is that for all values of x, what are the all values of x? It can have either 1 or -1. Okay, so first we write 1, then we write its probability, that is 1 by 2 plus -1 multiplied by its probability 1 by 2. What we get? 1 by 2 minus 1 by 2, that is 0. But does our variable takes a value 0? No. This domain of x contains only two discrete values. It cannot take 0. But depending upon this probability distribution function, we have estimated that if we will perform this experiment, if we will flip this coin for, let's say, 10 times, 100 times, 1000 times, we do not know that exact number, but if we'll keep doing that, based on this probability function, the final the estimated value that x will take is 0. Is that okay? Fine. So it is a possibility that the expected value that we calculate based on the probability density function is not does not lie in the domain of our random variable. That is completely possible, and it is completely true. Similarly, for continuous random variables, we can calculate their expectation using this formula. So x over d integration. Now instead of summation, we are doing integration because it is a continuous variable. For continuation variable, we'll do x px dx. All right, I'm not explaining dx to you, but as of now, it is not relevant. If required, I'll explain this to you. So as of now, try to understand this, that it is like just like in integrations, this denote very small deviation to x. That is what we do when we do integrations generally, right? Now next is, what is variance of a random variable? So now what this expected value gives us, it is like giving us a mean of our random variable. So let's say if our random variable is spread around this axis, what it will do, over all these values, it will try to give you a mean value, which is the most probable value that you will take. Or rather, it is trying to give you a center of the distribution of your random variable. Now what is variance? Variance is again the spread of this distribution. How will we calculate that spread? Using this formula. What is this? Expectation of this complete function. What is that function? For any value of x, subtract it with expectation of x, then take a square of it, collect all these values, and calculate expectation of that. So how we do that? We can calculate expectation of a function fx using this formula. If there is any function of x, the random variable x, then we will calculate its expectation using this, expected value using this. Summation of x over d fx probability such that x takes a value x. Okay, so this is what we'll be doing to calculate the variance of a random variable. Okay, we can also simplify this expression for computational purposes, and after simplification, this is the expression we get. All right, so variance is expectation of x square minus whole square of expectation of x. So this is very simple to calculate through a computer rather than this. Okay. Next, we are interested in covariance. Covariance of two random variables. So just like we studied correlation in statistics, now since we are talking about two distributions, so a random variable is not just two values or not just a set of values. Covariance is now a relationship between two different distributions, and such for that we use the term covariance. So how much x varies with y? We recall that we studied something like this, that when x goes up, y goes up. This was what we said, that they have a positive correlation. To some extent, this is what we are trying to understand, that how much x varies with y. That is covariance of xy. And this is the expression for that. I'm not going into the explanation or derivation of these expressions. They will take a lot of time, and we are not in a class of probability to understand all this. All of you must be having some university subject in your second year itself, by the name of engineering mathematics, or let's say probability and statistics for engineers, or maybe understanding data, or there are several names. But you must be having some subject where all these expressions must have been derived and explained to you. All right, but we'll not go into those derivations. We are just trying to revisit them so that we'll have them learned fresh when we need them for our machine learning algorithm. Okay. So the covariance of xy can be written as expectation of this complete expression, and in this expression has these two factors, where the first one is x minus expectation of x, and the other one is y minus expectation of y, which can also be rewritten as this, and this is fairly easy to be computed with a computer. Expectation of xy equals to expectation covariance of xy is equals to expectations of xy minus expectation of x multiplied with expectations of y. What covariance does? It describes dependence of variables, and if covariance is 0, then it would mean that expectations of xy is equals to expectation of x dot expectation of y, which means that these two variables do not define anything about each other. All right, and this is how we identify whether two different random variables are independent of each other or not. So if they are independent, we should not go ahead and try to learn the pattern between those variables, because that will be a waste of time. All right, and then later when we'll study something called principal component analysis, we will see that how this covariance can be used to understand the behavior of variables and predict values. All right, and based on this principal component analysis was the first algorithm that was very back ago, which is called eigenfaces. What this algorithm did? Face recognition. Long before the machine learning became famous. Oh, sorry. Long before the term machine learning became famous, or deep learning became famous, or we had good quality cameras or whatsoever, as back as that. Okay. So using this very basic concept of principal component analysis, some statisticians, they attempted to recognize faces using an algorithm called eigenfaces. So we'll also I'll, if the time permits, or if we could get one session, I will try to explain this particular algorithm to you. Okay. However, as of now I do not have it planned to discuss eigenfaces. However, we'll be discussing PC. That we will do. So all that we discussed today, is it clear? Any doubts from today's class? I'm open to them.